Howdy! Today I would like to present our RAL paper, Robot Risk Awareness by Formal Risk Reasoning and Planning. This work was done as part of my PhD thesis at Texas A&M University with Jan Duvik and Robin Murphy. Let's start with a motivating example, mine disaster borehole entry. The example is from 2007 Crandall Canyon mine response in Utah. The idea in the borehole entry is to insert a small robot into the borehole, drop the robot to the floor, and explore the affected area. The mission includes two regions, the borehole and the mine floor. In the borehole, the robot faces multiple risks: getting jammed due to small clearance, falling rocks due to the lack of casing in the borehole, drilling foam water, and debris, and the vertically hanging tether. Those are because of the borehole itself, so we say it's caused by state. Before reaching the second region, the robot needs to exit the borehole and transition into the mine floor. The mesh roof in the transition may interfere with hole exit. Tether may get tangled with the mesh roof. Also, transitioning from vertical mobility to operating on the mine floor may not be successful either. This is caused by taking the action of transitioning from borehole into mine floor. Assuming the robot reaches the mine floor, locomoting in unstable terrain due to mud and water may also trap the robot. Robot has to traverse soft gel tailings and foam, or even equipment. These are because of the mine floor itself, so based on state. Although the robot and tether has already passed through the borehole and mesh roof, further locomotion on the mine floor also requires continuous interaction between the tether and the borehole or mesh roof. Tether entanglement is still possible. This is not only because the robot is on the mine floor, it's also because it came through the borehole and mesh roof, so we call it because of the traverse. Due to all the risks the robot has to face, it failed at the mine response in all 4 runs. The robot was lost in the borehole during the last run. The failure rate of exploring the mine is 100%. So many risks the robot faces cause such a high failure rate. So motivated by this example, we want to answer the question, how can we formally define the risk the robot faces in unstructured or confined environments and represent the risk so that we can reason about it? We formally define risk as the probability of the robot not being able to finish the path. To our best knowledge, risk has never been formally defined in the literature. In existing works, risk was related with collision, crash, being detected, etc., and was implied as a metric that becomes larger when being closer to obstacle. Based on the idea of states in numerous existing works about risk, the robot's workspace is based on tessellation of the Cartesian space. Each tessellation is a viable or unviable state for the robot. A feasible path is composed of an ordered sequence of viable states. When the robot is executing the path, it faces multiple risk elements, which will possibly cause not being able to finish the path. Three different events are defined. F represents the event where the robot finishes the path. Fi is the event where the robot finishes state I. Fik is the event where risk K does not cause a failure at state I. The risk reasoning framework relies on three assumptions using propositional logic. We use probability theory to derive and represent risk. Using the first assumption, the probability of the robot finishes the path is the probability the robot finishes all states. Expanding this equation using probabilistic chain rule, the probability is the product of the probability of finishing each individual states given the previous states are finished. Note this is the probability of finishing state n given finishing state 0 to n minus 1. At state I, any one of the risk elements can cause state I not finished. This is our assumption too. Fi is logically equivalent to Fi1 and Fi2 and all the way to Fir. Given the robot finished state 0 to I minus 1 and comes to state I, if the robot will crash to obstacle or if the robot will get stuck in unstable terrain is independent. This is our assumption 3, conditional independence among individual risk elements. This allows us to take the individual events out and compute the product of the individual probabilities. We can write the equation in a more compact form. This term is the probability of risk K does not cause failure at state I, given the history. So the probability of F bar not finishing is just a complement of P of F. We plug in the equation from the last slide and then we can take complement of the individual probability as well. The probability of F bar is just the probability of not being able to finish the path, which is our risk definition, defined as risk of path P. The lower part is the probability of risk K causes failure at state I, given the history from state 0 to state I minus 1. This probability is defined as risk K of state I. It is a function of state 0 to state I. So we can write the equation from probability form to risk representation form. Probability of not F is the risk of path P, and the probability of risk element K causes failures at state I, given the history, is the risk K at Si. This equation is the risk representation based on our formal definition. From this equation, we can clearly see the dependencies on the history states. We call it longitudinal dependency, so finishing state is dependent on history. On the other hand, risk element causes failure is independent of each other, which we call lateral independence. This is our assumption and matches with most cases. To compare with the existing risk in the literature, risk at a state is dependent on history. This is reviewed by our formal reasoning. The entire sequence of state is termed as traverse. The most special case of history dependency is no dependency at all. We can relax the entire dependency in the equation. We call them locale-dependent risk elements. Specifically, if we only take dependency into last two states into the history, we call it action-dependent risk. Lastly, the most general state dependency is with the entire history. We name it traverse. We propose 16 risk elements, which belong to the three dependency categories. Please note that only 3 out of the 16 risk elements have been looked at as risk in the literature, and they all belong to the locale-dependent category. Furthermore, only one existing work has included 2 risk elements at a time, and used weighted sum to combine them. All other works only considered the effect from one risk element. Now we switch gears to talk about the risk-aware planning to find a minimum risk path under this risk framework. But apparently this is a very difficult task. If we look at the risk representation, we can see that the risk at a certain state cannot be uniquely determined by the state itself. It is dependent on history. Also, the risk of a path is not additive. Existing risk-aware planners assume optimal substructure and won't work under our history dependency and non-additivity. In the universe of all risk elements, our risk-aware planner can guarantee that minimum risk paths due to locale and action-dependent risk elements could be found. But for traverse-dependent risk elements, there's no guarantee for optimality. This is our risk-aware planning algorithm. Still based on graph search, the high-level idea is to augment each vertex V with directional components D. The algorithm is similar to Dijkstra's, but now each vertex is subdivided into multiple directions. While Dijkstra's is trying to close vertices, we are trying to close directions. We also evaluate the risk on the fly. Here are some examples. The conventional approach prefers the twisty path thinks it can only address state-dependent and additive risk, but the risk caused by extra turning and path length is overlooked. The proposed planner, however, finds a straight path safer, since it compromises state-dependent risk for action-dependent risk. However, not all the risk elements have only two state history dependency. It could be 3, 4, or n. Therefore, we could look deeper into the history. Using the intuitive graphical illustration and assuming full connectivity, we could divide one state into 4 directional components for 2-state lookback, 16 for 3, and so on. Then we could use a similar approach as the proposed risk-aware planner and find optimal paths for up to n states back in the history. For example, mud may stay on the robot wheel for at most 4 states, so a 4-state lookback is enough. However, all these are at the cost of computation. The complexity increases exponentially with respect to the history depth. We show our risk reasoning and risk-aware planning using an integrated demonstration as a duplication of a task in Fukushima Daiichi nuclear decommissioning. We fly a tethered UAV to 2 good viewpoints to visually assist a teleoperated ground robot. The risk of each is reasoned by our framework. We consider 6 risks: state-dependent distance to obstacle and visibility, action-dependent turn and action length, traverse-dependent tether length, and number of contexts. The tables show the risk value caused by each risk element at each state, and the total state risk. The risks for both paths come up to 0.714 for the red one and 0.575 for the green one. 10 trials each are conducted for both paths. The black trajectories in the figures on the right is from one of the successful trials for the red and green paths. Success or failure for each trial is listed, with failure causes specified. The figures on the right shows which trial fails at which state. For red paths, only 2 of 10 trials succeed. Most failures happen on the upper portion of the path. The major failure causes, collision with railings or oscillation, are largely because the UAV is trying to maneuver the complex path. The green path succeeds 4 out of 10 trials. Since it cuts through very close to the railings, collision and accidental formation of contacts with railings are the main failure reasons. Both failure rates are roughly reflected by the risk values. Looking at the risk values in the table and the frequency of failure in the figure, correlation exists between states with higher risk and higher failure frequency. This also means the proposed risk representation can approximately reflect failure rate in physical experiments, so the theory matches with practice. It is the similar case for green paths as well. Each individual number may not match perfectly with the failure frequency, but the general trend is clear. In conclusion, this work presents a formal risk reasoning framework based on propositional logic and probability theory, and also a risk-aware path planner that conforms with the newly proposed risk reasoning framework.